We will move to the next part of this particular topic. We are still overviewing some of the fundamentals of image processing, and we will start with the concept which is called segmentation. Now, a segmentation is partitioning of image pixels into meaningful non-overlapping sets. The binarization process, what we discussed earlier, it is a special case of this segmentation. In that case, we have only two such sets that we discussed. One is of the background, another one is foreground, but it could be extended to groups of pixels which are more than two levels. For example, we can consider a multi-level thresholding scheme. In the previous case, we have just only single thresholds. In a multi-level thresholds, we can have more than one threshold. Say, consider this particular image and its histogram, and let us consider we have selected these two thresholds. We can use the similar computations what we discussed earlier, particularly the Bayesian classification methods that can be extended further, and we can determine these thresholds automatically also, or manually by visualizing the modes you can also select these thresholds. In this particular case, let us consider there are three such intervals, and for each interval we assign a particular color to those pixels. There are three colors you can look at this particular image, and that is they are blue and green and yellow, and each color represents a segment of the image. As we can see from the intervals, say there are 0 to 60 and 61 to 119 and 120 to 255. These are the definitions of those non-overlapping intervals, and this is how the pixels are grouped into this particular image into three different segments. You can note that 0 to 60 corresponds to the darker values, which is the water channel here. 61 to 119 is the middle values. Usually these are the points which corresponds to this interval, and 120 to 255 they are the brighter values, and they corresponds to the yellow portions of the image. So, this is the blue zone, this is the green zone, and this is the yellow zone. So, one of the tasks of segmentation, even after segment grouping the pixels into different intervals, that is still remaining, and that is called component labeling. So, in this case we need to also partition the image pixels in the plane itself. So, it is a connected image pixels into meaningful non-overlapping sets. That is what is our objective. So, there we can use various neighborhood definition to define this connectedness. For example, we can consider the 4 neighborhood definition or 8 neighborhood definition in this respect. Say 4 neighbors are defined in this fashion. So, given a pixel, these are the positions of the neighboring pixels, and out of them these are the pixels which are called 4 neighbors. Suppose this is a location x and y, this is a coordinate location. So, this could be x, this should be x plus 1 y. So, this is its right neighbor. Similarly, x minus 1 y, this is its left neighbor, x y plus 1 its top neighbor, x y minus 1 its its bottom neighbor. So, these are the 4 neighbors of this pixel, and this neighborhood is called 4 neighborhood. Whereas, if I consider also the diagonal pixels, diagonal positions are also their neighbors. So, then this definition is an 8 neighborhood definition. So, you can have different such neighborhood definitions, and accordingly this connectivity will be also defined between two pixels. So, let us discuss a particular case when you want to get the components preserving the 8 connectivity of pixels. So, let us take this particular example. So, this is a small image, and each pixel value is represented by these numbers. So, this is a 4 by 4 image, for example. So, what we do, we can form a graph with edges between neighboring pixels having same levels, which say you consider every pixel is a node of this graph, and you form the edge when their neighbor, the neighbors have the same pixel values. So, for example, this is 20, 20, 20, 20. So, you can see that all these pixels, they form edges among between themselves, and similarly we can form edge between 50, 50 and these pixels in this form, and also say for 100, 100 this is the edge. For another case, this 20, 20 form an edge, and 100, 100 another edge. So, it gives a graphical representation of this particular image following the neighborhood definitions. So, now your task would be to find out the components of these graphs. You can use any graph traversal algorithms like breadth first search or depth first search, and by which you can find out each component and declare them as a segment. So, I have displayed here by different colors those segments. They are showing different components in this case. One of the interesting question what could be asked here, that whether you require explicit graph representation in this case, because you have already the image array, and the neighborhood definitions are already neighborhood definitions are very precise. They have a well organized structure. So, actually you do not require any graph representation. You can compute everything on this array itself to get these components. So, you can compute using only one image array itself. So, some of the examples of this processing, let me show you. Say these are the two images which we earlier displayed. So, this is the original image, and this is the segmented image into three segments, three classes of intervals. Now, we are forming the connected components from each segments. So, I will show you some of the prominent components in order of their number of pixels in those components. So, this is the largest component, and you can see that in this component we could get the river channel into one component itself. Similarly, you can have various other components. So, this should be corresponding to this part of the zone. This is a green segment. So, connected green segments are shown here. This is mostly showing you connected regions in this part, yellow segment part. So, you get brighter pixels, yellow segment parts from here, and in this way there are various other components could be also retrieved. I have shown only 6, but there are many other components which are possible in this image. One of the interesting question that I can ask you from this results itself, you need to be carefully observing you should observe these results. See, you can find out that though in the original image the river channel, there is a river channel, this is a river channel, and in the largest segment also you can get the corresponding area of the river channel, corresponding pixels to river channel, but part of the river channel is missing in this segment. So, can you tell that why this part is missing? So, this is a question you need to find out by yourselves, and you check why there is this information is missing in this part. So, let us now discuss another operations for this with the images, and we called these operations are computation of gradient values in the images. So, a gradient operation is defined in this way. So, image is a two-dimensional function. So, in a two-dimensional functions, a gradient vector is defined by the corresponding partial derivatives along two principal directions. So, this is a partial derivative with x and partial derivative of function with y, and they form a vector, and that is a gradient vector. So, computation of this gradient is quite simple and direct. We can use finite difference method, by which you can compute gradient along the x direction, which is simply the difference between the right neighbor and the pixel itself, and similarly we can compute the gradient along y direction. It is the difference between the top neighbor and the pixel itself. So, functional values at those positions is the difference. So, with these simple computations you can compute these gradients and you can get the gradient vector. These computations let me discuss in a more general framework. There is a motivation behind this that would be understood later on. Let us consider that these difference operations would be performed by a computation with mask. So, let us define a mask. In this case it is a mask of 1 into 2 elements. Mask is a kind of array. In this case it happens to be one dimensional array. So, the dimension is that there are you can say there are 2 rows and number of column is 1 in this case, and these values in the mask they represent the weights. So, what you need to do for computing the gradient along the vertical direction, you place this mask at every pixel positions. So, one of the points in the mask is corresponds to the central pixel positions, and that is shown here by this particular coordinate x y. So, you are placing this mask in the x y positions, and then what you are doing, you are performing the computation. So, we are performing the weighted sum of the pixel values of the corresponding with its neighbors where this mask is also present. So, once you place a mask here x y, so this should be multiplied by -1, then the functional value at x y plus 1 should be multiplied by 1. So, effectively if you take the sum, that would be the difference between these two values. So, the algorithm for this mask would be that you scan the image top to bottom and left to right, then at every point x y place the mask and compute this weighted sum, which means that as I mentioned that you multiply the weight with the corresponding functional value at those locations, and then you take the addition, take the sum of them, and that would give you the weighted sum, and then you replace the central value by this weighted sum. So, in this way you can compute the differences, finite differences along the vertical directions. Same computations can be carried out with this mask also, which computes that difference along the horizontal directions. So, to generalize this computation for making a robust gradient computation, what we can do, instead of computing the difference only with the right neighbor or top neighbor, we can consider a neighborhood region and find out the statistics of these finite differences in that region and take the mean of those mean of that distribution. So, in this case particularly, say we are representing the mask value. So, we are taking a 3 cross 3 mask, and this is the central positions, these x y positions. So, with respect to this position, we can compute finite differences along using these 2 pixels also, similarly using these 2 pixels and these pixels, this one and this one. So, there are, you can see 6 times we are computing these finite differences around its neighborhood, and each one would not be the same. They are different values, but it is expected that if there is a gradient directions, statistically I mean if you take the average, then the noise or the error would be reduced if you take the average of all these values. So, which is equivalent, these computations, since these are all linear combinations, these computations can be carried out by a single mask computation itself when the mask is designed in this fashion. So, you can note that what we are doing at every cell of the mask, we are simply adding the weights. So, 1 minus 1 becomes 0 here, this 1 is 1. So, in this way, this is the distribution of weights in the mask, and we can carry out the same computations with this mask and compute the corresponding horizontal gradients in this particular case, in the gradient in the horizontal direction. Similarly, gradient in the vertical direction also could be computed by this mask. Incidentally, these masks, 2 masks are called Prewitt operator in image processing, and as you understand that 6 times you have computed these gradients in a particular direction. There is another example of robust gradient computation. In this case, what we are doing, we are giving more weights to the central gradients than the off-centric gradients. So, for example, in the horizontal directions, when we are computing this gradient, we are giving weights of 2 here. So, weights are doubled compared to the off-centric rows. And once again, as I mentioned that every values of the cell can be computed by the sum of these corresponding values, and if I multiply them with the weights. So, the distribution of the weights in the mask will look like this. This is for the computation in the horizontal directions, and similarly for the vertical directions the distribution will be here in this case. So, this is the Sobel operator, and this gradient has been computed 8 times in this case. So, this is a 8 times direction. So, the results of these gradient operations let me show you here. Consider this is your original image, and if I compute the vertical gradients, I am showing those pixels where vertical gradients are very prominent. You can see those vertical bars of the fences, they become prominent in this particular image. For horizontal gradient, again the horizontal directional fences which are parallel to the ground, in those directions those fences are becoming more prominent. But if I consider the resultant of these two vectors by taking the magnitude of the vector itself, we will get all the h pixels in every directions, and the corresponding edge points or boundary points of different object surfaces, they become prominent in this particular image. This is how we compute the gradients. Let us generalize these computations with any arbitrary mask. That means we consider any arbitrary weight distribution, and this is an example of a 3×3 mask, but it could be of any dimension itself. So, if I consider weighted sum of the pixel values around its neighborhood, around the neighborhood of the central pixel, and we can represent these computations in this form. So, we are assuming that we are considering the functional values at the corresponding locations, and then multiplying its weights, and we are taking the sum of all these values, and that gives you the corresponding weighted sum, and which will replace the functional values in the processed image. So, this computation is nothing but a convolution operation, where at every pixel you are placing this mask and you are computing these weights and then replacing that functional value with this processed value. So, it is we have already you know the convolution operation. It is a operation meant for computing outputs given the input of a linear shift invariant system in this case, and this is the impulse response. So, these weights, they define the discrete impulse response in this case, which is also called filtering, because there is a frequency domain, transform domain interpretations, which I will discuss in the next lecture. So, this mask is sometimes called also filters. So, this is the filter response HXY. One example of this kind of filtering is noise filtering, where the mask values are shown here. You can see that every value is a positive, and it is a weighted combination of the neighboring values. Finally, sum of all these weights is equal to 1. So, this gives you a kind of low pass filtering action, and if I apply this operation, these convolution operations on this image with the same mask computations what we discussed, that is weighted sum of the weighted sum of the pixel values around its neighborhoods, and from there and replace the original pixel value by the processed pixel value, we will get an image something like this, where you can see that these noisy structures look little reduced in this case. A special case of this kind of filtering operation often used in the image processing tasks is called Gaussian smoothing. When the filter or the mask is computed, the weights of the mask is computed following a Gaussian distribution. So, you consider the origin of this distribution at the central pixels, and there is a width of the Gaussian distribution or standard deviation of the Gaussian distribution. Accordingly, the mask size also has to be determined to capture the Gaussian most of the functional values, significant functional values around its mask. So, we can perform. So, this is a symbol which is usually used for convolution operation. We denote it this computation of with the mask what we discussed by this simple operation, simple symbol, and this is what is the convolution operation. So, in this particular case, if the mask size is 9 cross 9 and your sigma value is 2, then using this Gaussian mask, if you by using this convolution operation, you can get a result like this. Median filtering is another kind of computation which is not which does not use convolution. Rather, it is a very simple to describe what it does. It computes the median value among the neighbors, among the neighboring pixels, and replaces the original value by this median value. It is a kind of nonlinear filtering operations, but this is a very effective method to reduce noise like spot noise kind of method or salt and pepper noise kind of noise, which are randomly the random dots which can be scattered over the images, and those could be minimized, those could be reduced mitigated using this kind of filtering. So, here we are at the end of our lecture on this fundamentals on image processing. So, as a summary, what we discussed in this particular lecture, that we can summarize it, that images, they are formed by optical camera, and we see that the mapping of 2-dimensional, 3-dimensional points to 2-dimensional points, that takes place through a kind of projection which is known as perspective projection. So, rule of projection we discussed, that in this case a point from a scene point, from a 3-dimensional point, you have to draw a straight line which passes through a particular point which is known as center of projections, and which hits the image plane. That point of intersection defines the corresponding image point. That is what is perspective projection. Then we have discussed different operations in image processing. Some of them are, say, binarization, and in binarization particularly we discussed the thresholding operation. Then we discussed also contrast enhancement, we discussed segmentation and a special task of segmentation of say component leveling. We also discussed gradient computation, where we have discussed how edges could be computed, and convolution operations. In the convolution operation, we also introduced the concept of filtering, which is equivalently called filtering, and it is a computation with a mask. A mask consists of weights in its cells, and that weighted sum gives you corresponding distribution. And then we also discussed median filtering at the end. So, here let me stop. Thank you very much for your listening.